Good day, esteemed researchers and curious minds tuning in from around the globe. We delve into the fascinating world of language model performance with our study, Observational Scaling Laws, and the Predictability of Language Model Performance. We explore the intriguing complexities of fitting observational scaling laws, analyze metadata to understand model performance, and tackle the challenges of evaluating proprietary models. Join us as we unravel these insights and more. Let's embark on this intellectual journey together. Our research is driven by the motivation to fit observational scaling laws for a variety of models. We aim to provide a comprehensive comparison and evaluation of these models, which include both standard and instruction-tuned models. These models have been evaluated on benchmarks such as AgentBench and AgentBoard, providing a rich dataset for our analysis. However, we've identified some challenges with existing approaches. For instance, proprietary models like GPT and Claude pose evaluation difficulties due to the lack of access to likelihood scores. Additionally, the complexities in data curation for instruction tuning present challenges in estimating the data for instruction tuning or additional fine-tuning. Despite these challenges, our research strives to provide a robust and comprehensive analysis of these models, shedding light on their strengths and weaknesses. This will ultimately contribute to the development of more effective and efficient models in the future. We're diving into a fascinating problem today, understanding the performance of instruction-tuned models through the lens of metadata analysis. This is crucial because it allows us to make sense of the vast landscape of models, from GPT to Claude, Llama 2 Chat to Open Assistant, and many more. Our motivation here is to fit what we call observational scaling laws. These laws provide a systematic way to compare and evaluate models. They take into account factors such as the number of model parameters and the amount of pre-training tokens, giving us a comprehensive view of each model's capabilities. Take a look at the figure on the screen. It provides an overview of these observational scaling laws. By fitting these laws, we can better understand the performance of different models and make more informed decisions about which models to use or further develop. In essence, we're creating a roadmap to navigate the complex terrain of instruction-tuned models. This is not just an academic exercise, but a practical tool that can guide us in the real-world application of these models. We face a specific challenge in evaluating proprietary models like GPT and Claude, as we often lack access to likelihood scores. This issue is further complicated by the complexities in data curation for instruction tuning, making it difficult to estimate data for instruction tuning or additional fine-tuning. Despite these challenges, various models and evaluations have been attempted, but a unified protocol for evaluation remains elusive. To address these issues, we propose several improvements. First, we introduce Algorithm A.1, designed to fit observational scaling laws. This algorithm allows us to systematically analyze and compare different models. Additionally, we propose a method for estimating training FLOPs, denoted as C, using the formula C approximately equals 6ND. This approach provides a simple yet effective way to estimate the computational resources required for training different models. These proposed improvements aim to standardize and simplify the evaluation process, making it more accessible and understandable for researchers across different levels of experience. Our research introduces a key novelty in the estimation of the parameter D for continually pre-trained models. Instead of just considering the initial pre-training tokens, we also incorporate the additional continual pre-training tokens into our calculation. This approach provides a more accurate representation of the model's learning process, taking into account the ongoing refinement and expansion of its knowledge base. This is a significant step forward in our understanding of how these models evolve and improve over time. Our research aims to fit observational scaling laws for a variety of models. We've developed an algorithm referred to as Algorithm A.1 that aids in this process. To implement this algorithm, we've collected data on model parameters and pre-training tokens for each model under consideration. We then estimate the training FLOPs, represented as C, using the formula C, is approximately equal to 6 times the product of the number of model parameters, N, and the amount of pre-training tokens, D. In cases where models have undergone continual pre-training, we adjust our estimates of D to include both pre-training tokens and additional continual pre-training tokens. Our focus is on instruction-tuned models, and we've evaluated these models on specific benchmarks. We've used standard language model evaluations for these instruction-tuned models. For proprietary models, we've collected official results from their respective papers and documentation. In summary, our research involves a comprehensive approach to fitting observational scaling laws, taking into account various factors such as model parameters, pre-training tokens, and continual pre-training. We've applied this approach to both open and proprietary models and have collected a wealth of data to support our findings. In our research, we've taken a comprehensive approach to evaluate instruction-tuned models. We've gathered ELO scores from Chatbot Arena 3, providing a unique perspective on the instruction-following capabilities of these models. This data, however, was not used for our downstream predictions, but serves as a valuable reference. We've also delved into the technical aspects of these models. We've collected metadata and benchmark results, offering a detailed look at their performance and characteristics. You'll find this information neatly compiled in tables B.1 and B.2. This data collection includes both open models and proprietary ones like GPT and Claude, for which we've gathered official results from their respective papers and documentation. This comprehensive approach allows us to better understand the strengths and weaknesses of these models and to identify potential areas for future research and development. Diving into the technical results, we've gathered metadata for a variety of models, which you can find in tables B.1 and B.2. This includes models like GPT, Claude, and Llama 2 Chat, among others. We've also collected benchmark results for these models, providing a comparative view of their performance on tasks such as MMLU, ARCC, and HellaSwag. In addition, we've gathered ELO scores from Chatbot Arena 3 to assess the instruction-following capabilities of these instruction-tuned models. This gives us a unique perspective on how well these models can follow instructions in a conversational setting. Now, what do these results imply? The metadata we've collected offers a comprehensive comparison and evaluation of different models. It allows us to understand the strengths and weaknesses of each model and how they stack up against each other. The benchmark results provide insights into the performance of different models on various tasks, giving us a clear picture of their capabilities. Lastly, the ELO scores serve as an indicator of the instruction-following capabilities of instruction-tuned models. This is crucial as it helps us understand how well these models can understand and follow instructions, a key aspect of their functionality. In summary, our results provide a comprehensive overview of various models, their performance on different tasks, and their ability to follow instructions. In our research, we've made several key contributions. We've developed a detailed algorithm, known as Algorithm A.1, which is instrumental in fitting observational scaling laws. This algorithm has been applied to a variety of models, allowing us to gather and analyze their metadata. Our study also includes a comprehensive collection of instruction-tuned models. These models have been evaluated using specific benchmarks, such as Agent Bench and Agent Board, providing us with valuable insights into their performance and capabilities. Lastly, we've provided a comprehensive comparison and evaluation of different models. This comparison not only highlights the strengths and weaknesses of each model, but also provides a roadmap for future research in this field. The figure displayed here represents PC1 as a smooth capability measure, further illustrating the effectiveness of our approach.